Welcome to this episode of Eureka and to the Sunset channel. In this episode, we are going to have a interesting conversation with Dr. Pushpavanam. He is with the Indian Institute of Technology, Madras, and he is the Institute Chair at the Department of Chemical Engineering at that institute. Sir, thank you for being with us in this show. I mean, this is a show where we highlight science happening in various Indian institutions to our audience through this medium of Sunset team. In this episode, we are very thankful that you have been here. So let me start with this question that mostly I ask most of our participants, which is, I'm sure you have had little more than 3 decades of experience in your academic career. So suppose if I ask you, what would be your 3, I mean, let's just take 3 to begin with, let's say, 3 interesting areas of work that you have worked on. What would you list them as?
So, thank you for having me on the show. Yeah. I mean, it's very nice to be here with you. And I think this is a good platform for me to talk about my work and reach to the young generation of scientists. And I hope what I say is they find it inspiring. I've been in academia for close to 3 decades. Mm-hmm. And when I started my career in IIT Kanpur, mm-hmm. I was working in the broad area of nonlinear dynamics.
Okay.
Mm. And to tell you, give a practical example of where that can be used. If you look at, and what I also want to show here is the versatility of a discipline like chemical engineering.
Okay.
And I think before I answer your direct question as to what the 3 areas are, which I think we've made good contributions in, what I like to emphasize here is today, I mean, science is all mingled. There are no strong borders, and every research is becoming extremely interdisciplinary. Consequently, I just want to show by way of some of the work that we are doing, there are implications and ramifications in a whole variety of subjects. So the area of nonlinear dynamics is one such area. And one of the things which we have observed in nature is that the eggs of species, when they hatch, and the sex of the hatchling is extremely dependent upon the temperature.
Yeah.
And there are some hatchlings which would be predominantly female at a low temperature and predominantly male at a higher temperature range. Okay. And it could be the other way as well.
Yeah.
And you could have hatchlings which would go from predominantly female to male and then back to female. So in nature, all this is observed, and we are talking about a temperature window of about 3 or 4 degrees.
Okay.
Because that's the incubation temperature.
Yeah.
And so this is a very curious phenomenon. And I have worked in trying to understand what has actually what causes this particular temperature dependent sex determination. So basically the temperature of the environment influences the sex of the hatchling.
Okay.
And this is an example of nonlinear dynamics which comes into the picture. There are biochemical reactions which are taking place inside the species in the egg, and these chemical reactions are actually responsible depending upon the enzymes which are secreted, whether it is a testosterone or a estrogen. Depending on those levels of these enzymes, the testosterone and estrogen, you can decide whether it's going to be male or female.
So can we move on to any other area which you think you feel very happy that you worked in that area, and then you feel satisfaction of explore that area?
One of the other areas made significant contributions is in the area of coal gasification.
Okay.
And the idea is, what we require is a clean source of energy or fuel. And coal, when you burn it, you don't necessarily get a clean source of energy. There's a lot of dust involved, there's a lot of particulate matter. And so what we wanted to do is, and what is done normally is, to convert this coal into a mixture of gases, carbon monoxide and hydrogen. And this is called synthesis gas. And this has a lot of calorific value.
Okay.
And we have basically, and there are many different chemicals which are used as gasifying agents. For example, oxygen is used, steam is used as a gasifying agent. Sometimes people use carbon monoxide. Now, what we did is use basic thermodynamics and try to find out performance charts, which basically tell you for a particular kind of feedstock, for a particular kind of coal, for a particular kind of biomass, what would be a good gasifying agent.
Okay.
Or if you know what the gasifying agent is, what would be the composition of the product which is coming out.
Okay. Okay.
So, I mean, this is the results we got were very powerful, and they would aid a person who is building a plant or designing a plant in making right choices. Okay. And that's why I find this work to be very satisfying.
Coal is a fuel, and finally the gasified product is also a fuel. So why do I need to convert one fuel into another fuel? In fact, perhaps maybe I'll be losing some, let's say, energy in this conversation, conversion. So why do we need to gasify?
Yeah. So I think one way to look at it is, it depends. See, the Indian coal, for example, has a very high ash content.
Okay.
And if you were to burn it directly into carbon monoxide, just combust it, as is done in typical power plants and boilers, there's a lot of particulate matter, fly ash, which is generated in the process, and that is a source of pollution.
Okay.
So that's what I mean by saying that the direct combustion is not clean, because there is a component of atmospheric pollution which comes in. Whereas when you gasify it, I mean, you have the syngas, and then you use that, and you end up, you don't have any particulate matter. So that's one of the reasons why you call it a clean source of energy, the syngas. And the other thing is, the syngas can be used for a whole variety of other applications as well. You could convert the coal to other chemicals which possibly have more commercial value. So that's a starting point for a lot of synthesis, a lot of organic compounds, for example.
Okay. Okay.
And so syngas has a commercial value also.
Much beyond as a fuel. I mean, not just only as fuel, but as a feedstock to many other production, right? Yeah.
Exactly. Exactly. For example, it is used as a feedstock for methanol synthesis. And today people are talking about, an economy which is based on methanol. So it can be used as a feedstock for a whole bunch of things.
Okay.
A whole bunch of hydrocarbons.
Yeah. I mean, I vaguely remember reading in some history of technology work that around the time of Second World War, or a little bit before the Second World War, gasification was an in thing. I mean, wood was gasified and the gas was used for transport.
Yeah.
In fact, buses were operated with that. So there are people who say that that's not a technology that we should forget, but keep in mind. So as somebody who is working on that area, can you slightly elaborate on this, if you don't mind?
So I think we've been trying to see, most of the work that we've been doing has been fundamental. There are other countries in the world where people have actually put up gasifying plants, like South Africa, for example.
Okay.
There are gasifying plants which are actually running and which are commercially viable. In India, we are yet to put a large-scale gasifier
Okay.
of commercial significance.
Uh-huh.
And we are, going towards, because there was some talk about doing this some time back, but now the emphasis has shifted more towards solar and green energy from that source. So the point I'm trying to make here is there are small gasifying units. What we've done in India is in states like Bihar, there are gasifying units which are small scale, which are used to power small households or apartment complex, for example. People have done that, or basically in villages.
Okay.
In a village, people have used gasifiers for supplying energy. But we are yet to put a large-scale plant.
Okay.
Okay. And
well, that's
that will happen soon.
That's still a potential area where one has a lot of possibilities. Not only coal, but also other kinds of biomass also can be gasified, right?
So what we are doing is, because of this drawback of this Indian coal of having high ash content, we are mixing it with other compounds like pet coke, which comes from a refinery. This pet coke has absolutely no ash. So one way to effectively reduce the ash content is to mix it with pet coke and then gasify this mixture of pet coke and Indian coal.
Okay.
So that would give you a better product. So our theoretical work shows that that is possible, but then we need to develop this to a large-scale unit.
Okay. Okay. Very nice. Very nice. I think now we'll move to a little bit different area. Like we started talking about three areas. So the third one that comes to my mind is something that was there in media recently. That is a paper-based technology to detect antibiotics in water.
Yeah.
Sewage water in particular. So which also in an indication of antibiotic abuse or possibility of pollution and so on and so forth. So can you tell us about what is this particular innovation?
Sure. But if you allow me, I will go back a little bit more.
Yeah.
And because we got to this point because of some other work which we were doing.
Yeah. Yeah.
If there was a revolution in the computer science industry.
Okay.
So when I was a student, for example, I used to run my computer programs on these gigantic machines.
Yeah.
Which are this IBM computer is what we had, and we used to write code in that and run these machines. And they were very powerful computers, and the machines would occupy a lot of space, big area. And with the revolution in the electronics industry, for the same computing power, we could now do it in a small laptop or a desktop.
Yeah.
We wanted to basically do something similar, and in the chemical engineering field. So normally when you talk about a chemical plant, one is thinking about all these big factories with big distillation columns and big reactors. And the idea was, can you actually shrink the size of all of this into a lab, which could be on your laptop, the size of a laptop. Basically, we used to call it a lab on chip.
Okay.
So can you basically synthesize whatever you're doing this large scale, can you do it in a small plant, which could be possibly you can carry it with you whenever you want to go, wherever you want to go.
Okay.
So can you do a shrinking of the chemical factory?
Okay. Okay.
Like you could do for in the electronics industry.
Yeah. Okay. Some kind of a miniaturization.
That's basically what miniaturizing without compromising on efficiency and efficacy.
Yeah.
So what we call process intensification. That's the technical word we use. You want to carry out the same thing on a small scale. So basically, the application which you were talking about is the sensor development. But what we need to do here is we need to, comes in the broad area of microfluidics.
Okay. Microfluidics.
And what do I mean by microfluidics is when you have fluids flowing in a channel which has a size which is less than 1 millimeter
Okay.
or 1000 microns. So if you have a pipe which is less than 1 millimeter in diameter, and if you have fluid flowing through it, that's basically a microfluidic system.
Mm-hmm.
So there are a lot of advantages of going towards a microfluidic system when you carry out a chemical reaction. We were talking about this exothermic reaction sometime back.
Yeah.
When you have an exothermic reaction, in a microfluidic reactor, the surface area available is much higher compared to the surface area per unit volume is much higher in a microfluidic system. So the heat that is liberated by the exothermic reaction gets quickly dissipated to the environment. So you can actually carry out reactions very efficiently and safely in a microfluidic system. The challenge here is that the surface tension forces are very important, the interfacial tension. Okay. And what we can do is we can control this interface tension by adding things like surfactants and control the behavior. Now, this becomes important when you're looking at an application.
Yeah.
So the work which we were looking at in the microfluidics area is basically twofold. One was we were looking at understanding how do liquids, multi-phase systems flow in a microfluidic reactor, for example.
Okay.
And if there's a chemical reaction, how does that behave? Things like that. So the point is, when you go down to the small scale, the physics becomes different. Okay, as opposed to the large scale, where you have a large scale reactor where you are able to mix and you can get what we call turbulent flow.
Yeah, yeah.
Now, if you are interested in carrying out a chemical reaction in a millifluidic reactor, in a microfluidic reactor, you want to make sure that there is good mixing.
Yeah, yeah.
Because only if they mix, the two chemicals are going, like nitrogen and hydrogen will react and form ammonia.
Yeah.
So, but what we are, one of the challenges we do address is how to improve mixing in the system.
Okay.
By looking at designs of the microfluidic reactor.
Okay.
For example, we can curve the reactor and try to exploit some natural features of the flow. In a big reactor, I can put a stirrer and I can mix.
Yeah, yeah.
And I can get good mixing. But here I can't put a stirrer. So there are ways by which I can change the geometry. I can exploit the properties of the fluids, like electric, and impose an electric field, for example, and then try to get mixing. So you need to have a good understanding of the physics.
Okay.
To come up and develop these reactors. So that's how we started. We did a lot of work trying to understand the physics.
Okay.
Which are prevailing at the small scales, small length scales that we have. Then the question is, okay, I mean, but when we do all these experiments in the lab and do all the calculations in the lab, we are actually using pumps to flow the two liquids. So the question is whether, since anyway we have miniaturized the system, is it possible to actually think of applications which will help us do an on-site measurement of quantities? Say, for example, if you want to measure the presence of pollutants in a wastewater stream, you want to take the sample, possibly go to a lab and get it tested.
Yeah.
And you would use a sophisticated instrument like HPLC or a GCMS or something and get your results. But, so the question we were asking is it possible to actually do an on-site measurement and find out whether the water sample has, heavy metals?
Okay.
Does it have antibiotics? And that's how we started thinking or looking at paper. I mean, people have looked at paper-based microfluidics in the earlier. And what we do here is exploit the fact that the paper is basically made of cellulose fibers.
Yeah.
And there is a gap between these fibers, which is also of the order of microns. And the fluid is going to flow through this gap between the fibers.
Okay.
So basically, a paper is something like a microfluidic device, because there are, intrinsic microchannels in the system, in the fiber, in the paper.
Yeah.
And if you remember, we used to have this blotting paper.
Yes.
When you have a blotting paper and you drop ink on it, the entire paper gets smudged, and the ink spreads all over the place. Or if there is ink which is falling, you will just take some blotting paper and keep it, and the blotting paper soaks the ink, and you basically remove the drop of the smudge. And this is happening because of the wicking action which is present in the blotting paper. So basically, surface tension forces are very high, and they actually suck the liquid. Okay, so what we can do is we can exploit the fact that the paper has a wicking action. You don't need to have pumps to pump your liquid.
Okay.
The liquid is going to flow on its own because of what we call capillary forces, what we call surface tension. The only challenge was we need to make sure that the liquid flow is occurring in a particular direction. That is, I want to make sure that I have control over the direction in which my liquid is flowing. I don't want the liquid to flow randomly. I want it to go from one place to another place. And the way you do that is you may render this paper, parts of the paper, hydrophobic, right? Which is, hydrophobic means it hates water. So one way to make the paper hydrophobic is to just take wax and you rub wax on it. So water is not going to go, because water and wax don't like each other. And so if you take a paper and if you make a small rectangle with a small the gap in between, so water will be confined to that space. And so people have done wax printing. People have, but there are challenges. The quality of the print is not very good when you do wax printing, and there are other methods which people have used. What we did in this work is we used a commercially available laser printer. I want to emphasize it was the black and white printer.
Okay.
And the toner of this printer has some amount of wax, and it also has a resin, which and this particular combination we have not done anything to modify this, because people have used laser printers in the past. They've changed the ink which comes with the laser printer cartridge. But so we used a naturally occurring laser printer as it is. We have printed it on the paper, and you can print using any software package like MS Word and the design that you want for doing a particular chemical test. And you can design certain regions where you don't want water to flow, certain regions where you want the liquid to flow, and you can make the pattern that you want, and then you have your sensor.
Okay.
What we do here is we coat the paper with a particular chemical, and then we add the sample which we want to analyze. Now, there's a chemical reaction between the sample and this chemical which we have coated, and this normally results in a color change.
Okay.
And so we call it a colorimetric sensor. And this color change is used to confirm the presence of a particular pollutant. So the chemical with which you are coating will depend upon the particular pollutant which you want to measure. It has to be selective to that particular chemical which you're trying to measure.
Hmm.
It has to be sensitive to it so that you can also measure low concentrations which are prevailing.
Mm-hmm.
And at the end of the day, it has to be affordable.
Okay.
So when you are actually doing this thing on a paper-based device, you can take it to the field. The paper-based device already has
the coating,
the coating of for a particular chemical that you are interested in, and you can do the test on site. So there's a lot of point of care diagnostics. Is what we call point. You can do on-site environmental monitoring.
Okay.
I mean, to give you a very simple example, I mean, almost everybody in India today has this glucometer to measure sugar levels at their home. Somebody or the other is diabetic. So that is an example of point of care diagnostics. Yeah, and it is also a microfluidic device, but the principle is not colorimetry. It is based on some electrochemical sensing.
Yes.
That's the difference. But it's a microfluidic device.
Okay. So this is a very, very interesting innovation that you talked about, that how using the principle of microfluidics, that you can create devices, sensor devices, which can sense. I mean, right now we have done for one particular aspect, let's say antibiotics. Same thing can be done for maybe heavy metals or other kinds of pollutant that we are interested. Yes. Right? I mean, not only pollutants, maybe even for other things, like you want to find out water quality. One can extend the same principle to multiple areas. That's what you are pointing out, right?
So, no, the applications are very diverse. For example, we were looking at developing, we are in fact working towards developing a sensor which will help in detecting cervical cancer in ladies.
Okay.
And I think that is something which hopefully will make some good progress in the recent future. Okay. So that would be something which would give a result, again, based on a colorimetric principle, but there's a biochemical aspect to it. Today, there is the other problem of pesticides, which people use in agriculture. And, what people want to do is, you may want to find out whether the cauliflower or the carrot that you are actually buying in the market has pesticides on it. So is it possible to come up with a paper-based device which you can basically use to find out the pesticide levels in these vegetables, in food products? So I think there are several applications which are there. Then you also have applications. Somebody was asking me, the poultry is fed a lot of antibiotics. So is it possible to find out whether the chicken he's buying in the market has antibiotics or is free of antibiotics? Because he doesn't want to consume the antibiotics through the chicken. So there are definitely a lot of applications which are there. And so I think it's a question of using the principle and then getting the application. And to do applied work, I think you need to have strong fundamentals. And strong fundamentals is what I believe is absolutely important. And that's what helps you come to these diverse applications. It helps you see connections between different things. It's not that the sensor is only for metals, it's only for antibiotics. It can be used for a whole bunch of things as long as the concept is clear.
Thank you. And I think because of want of time, we may have to end this interview here. It's been a very wonderful conversation. A lot of very interesting stuff we understood, from nonlinear dynamics to microfluidics, and in between also how coal gasification can help in reducing pollution, and at the same time draw clean energy from a source which usually we will dismiss as polluting source of energy. Maybe we will have to live with coal for some time, so perhaps we need to find ways of making it as clean as possible. And you are talking about coal gasification. It's been a very wonderful conversation. Thank you for being with us in the show. And with this, we'll end this program today, but keep watching Eureka. We'll come back with another episode next week, same time.